I hope you enjoy the workshop today. It's time to relax to listen to the talk. So I will talk about the actual research work we did. It's a quantum simulation of jet quenching. Let's see if I can do it. So first, what is quantum simulation? So first, if you think about a state, a quantum state, as you have learned in like quantum mechanics, the time evolution in the quantum dynamics is giving us the following. So this is just writing the time-dependent Schrödinger equation in a different way. So this is the initial state, the state and the Ti, and then with the unitary evolution operator, it becomes the final state. So this is actually the past ordered integral, and the Hamiltonian depends on time. If the Hamiltonian is a constant, this whole part would just reduce to exponential to negative IH. So you can just think about the exponential Hamiltonian. And so the Hamiltonian is a solution, and it contains all the information of the system, like how the particle interact with each other and what potential is like. So this kind of it's kind of intuitive that you have the information system in the Hamiltonian, and you have the initial state, and with the evolution, you get the final state. And okay, and so for physical system, if we start with some initial state in the physics, and then after a unitary evolution, it will get to a final state. So this is a dynamical process. And what quantum simulation do is actually just a compilation or a mapping. So if we do this on a quantum computer, so we can encode the state, the quantum state, to the qubits. Like here. Oh, okay, sorry. So like here, as you did in the exercise, you encode the integer 0 and 1 to qubit, right? And it can be like more complicated to include more information. So here I can encode a state to the multiple qubits. And then to get a specific initial state by amount, one could apply some gates and to get the initial state. And then this unitary evolution can be compiled and the gate sequence on the quantum computer. And so this part operates as a unitary evolution, and in the end, you get the final state. And with the final state, one can do a measurement, and this would allow us to extract some physical quantities and observables. So this is the idea of quantum simulation. Then a natural question follows is that, so we know how to solve it. We know how to solve the Schrödinger equation with paper and pen or with a powerful computer. Why do we bother to do it on quantum computer? So one big reason is that there is a potential exponential speed up in doing this calculation on the quantum computer. So if you think about the system with a degree of freedom of ND, then the Hamiltonian has a dimension of ND squared. And more than that, we are doing exponential of the Hamiltonian. And if we encode this to a quantum computer, then the dimension of the qubit we need is a log of the ND. And then the number of gate sequence ideally should be a polynomial size. So there is an exponential speed up. So that's one big reason why we try to do a quantum simulation on the computer. Okay. So now this is a quantum simulation. And what is jet quenching? Because I'm going to talk about the quantum simulation of jet quenching. You may not heard of jet quenching before, but you might know what a jet is. So the essential idea of it is that here the jet stands for a rapid stream of matter. And you might also know what quenching means. So this is in the process of forging a salt. So when you forge a salt, you heat the metal to a very high temperature, and all of a sudden you put it into the cold water. So this quenching means a rapid cooling process where a hot object loses energy. Okay, so putting together jet quenching in the heavy ion physics, so what the jet means is that a cone-shaped beam of energetic particles. So recall that the ideal jet is a rapid flow of matter. So here the jet is energetic particles. And then there's a hot medium that is created when you collide two heavy ions with high energy. And when the jet goes through the medium, it will lose energy because it will interact with the medium. So this phenomenon is called jet quenching because you have a jet and it lose energy. So that's the jet quenching. And why are we interested in jet quenching? Because so this jet it goes through the medium. So if we study the property of the jet, like how jets evolve, we could get some clue about the property of the medium. And why are we interested in the media created in heavy ion collision? Because this could shed some light on how the matter of the universe is created in the beginning. So that's the big idea of this. And so that's the basic idea of this work. So to study jet quenching on the quantum computer, so first in the following, I'll first introduce the theoretical setup of jet quenching we did, and then introduce the quantum simulation algorithm. And then together we can calculate some observations from the simulation. So the theoretical setup is essentially very simple. So if you think about a highly energetic quark, so that's the jet, and they're moving with high energy, so this is conversion. So it will go through this medium. So this is the medium created in the heavy ion collision. That's the initial time, that's the final time. So we consider the evolution of this process. And so this is the written previously, the evolution of the state. And for this problem, we are looking at the Hamiltonian contains two parts. One is the kinetic energy, because the quark itself has some momentum. And then the second piece is the interaction of the jet with the medium. That's the Hamiltonian. This is the setup. And then to do quantum simulation algorithm, there are 5 generic steps. So first you need to give some input. So this we already did. So that's the system Hamiltonian that I showed you in the previous slides. So next we are going to do encoding. So we need to encode the problem we want to study to the language of the quantum calculation. And then we will prepare the initial state, do a time evolution, and in the end, do the measurement. So the encoding is just a mapping from the physical basis state to the qubit state. So the physical state here we are interested in has the different transverse momentum mode here, and also the colors. This is not the actual visible color, but this is the you can think about it as a quantum number. So here it corresponds to say equal to 0 and 1. And so those physical basis states run over the different transverse momentum mode and color. And we would like to encode this to the qubits that will rise as the binary bits of 0 and 1. So just for example, if we are encoding some momentum mode with the quantum number 1 and 3, so px and pi 1 to 3. First, you can write it into its binary representation, so that's a 0, 1, and 1, 1. And then you can encode it to the qubits on the circuit. So this is the idea of encoding, it's just a matching. And then when you know how to encode the basis states to the qubits, then for our quantum state in general, it's a superposition of different basis states. So this beta is the basis coefficients. And so in principle, one could prepare any state as the initial state. But here in this work, since we're interested in how the transverse momentum change of the state, so we prepare the initial state with 0 transverse momentum. And then for the color, we choose a fully balanced superposed color state. Now we have going all day and you have done the exercise. Do you know how to prepare this kind of state with a 0 initial state? Which gate. Here you get state.
Oh,
Yes, great. Yes, that's just use a hand gate to 0, so you get that state. And then with the initial state and the encoding, we can do the time evolution. So the time evolution is to decompose the unitary evolution operator into many small time pieces. Because it is difficult to do the whole evolution at one time because the Hamiltonian depends on time. But if you chop it into the pieces and different time step, then at each time step, when the time step is small enough, then you can treat the Hamiltonian as a constant within each time step. So that would allow you to do the calculation more straightforward. So this is the method we are using. And then within each time step, recall that our Hamiltonian here has both kinetic energy part and the interaction with the interaction with the medium. And due to the property of the Hamiltonian interaction here, so this kinetic energy part is more efficient to do the calculation in the momentum space, while the interaction with the medium, so that one is local in coordinate space, so it's more efficient to do the calculation in coordinate space. And so to take advantage of both their properties, we put in a, do you know what's the transformation that could let you go between momentum space and the coordinate space? Okay, the Fourier transformation, yes. And then on the quantum circuit, that's the quantum Fourier transform. And it itself is also a research area. So that's the time evolution. And in the end, when you do the time evolution, you get the final state. Now we want to measure the final state. So the state itself, so in the basis, so beta just means different basis states. It's a superposition of different basis states. So here it means different momentum mode. And when you do a measurement, what happens is that the state will collapse to one of the eigenstate, right? And this means if I write out it in the qubit, so this Q01, it each can take 1 or 0. Once it's measured, it also collapses to one of the state. So this means if I want to look at how the state is distributed in the momentum space, I need to do multiple measurements because each time I only get the state collapse to one of the momentum mode, right? As you did in the exercise, you need multiple shots to get the probability. So that's how we do the measurement. So we perform multiple measurements, which is called shots. And then we are able to reconstruct the distribution of the state. So this diagram is a histogram. So the vertical, so the horizontal corresponds to different momentum mode. And the vertical one is the number of counts. So when you do one measurement, the state will collapse in one of the square. But when you do 3,200 shots, you get a distribution. And so the red error bar is the statistical uncertainty. And when you increase the number of shots, you see the relative size of the red error bar largely decreases. So meaning with the increase in number of shots, the results we get are more accurate. Yes.
The statistical uncertainty depends on the simulator that you use, or because how do you get to it?
How do so we use we assume so since each measurement is independent, so it's the probability follows the Poisson distribution. So this uncertainty depends on the number of events that fall into each beam. Yes.
We use the ideal simulator, the quantum simulator.
Sorry.
We use the ideal quantum simulator.
Okay.
So
we have noise.
Yeah. This is not from noise. This is just the statistical uncertainty. It's like when you when you toss a coin, you count the number of up and downs. The more number you do it, it's more accurate. Yeah, so that's the. And then from the histogram, so this is the transfer momentum tip of the sphere. We can also construct the two-dimensional transverse momentum distribution. So what you can get from here is that, so we prepare the initial state and the zero momentum state, meaning the initial state is only in the center, so 0, 0. And after the interaction is median, after the evolution, the simulation on the circuit, the final state is distributed. So the momentum spread out, and this is the momentum brought in. And yeah, so that's the result. And then following the previous question about the noise, so in the actual quantum computer, there are actually quantum noise there. So the exercise like we did today on the quantum simulator, there's no noise, but in the actual calculation of the quantum computer, there could be noise. So here we also simulate those noise and also use the IBM also backend. When there are noise there, you see the result of the deviate from the one. So the red one is without noise. So, and without noise, the result kind of is close to what is expected analytically. And the level of noise increase, the result gets further away from what is expected or from the physical one. So this means if you look at the star one, the noise overwhelms physics. So one could hardly get any clue on the physics if the noise is too much. But this is what we get with the current setup and the computer. So there's still a long way to go. And that's it. So here I introduced our work on the quantum simulation of jet quenching. If you are interested, you can read our paper. And the future plan following is that what we did is just the jet is just a single part, but it would be more interesting to put in more particle, like to put in one more gluon there. Because as I introduced in the beginning, one big advantage of doing quantum simulation is there's an exponential speed up, right? So if your problem is more complicated, if you have more particle, then this speed up would be more valuable. So that's one direction of our work. And then the other direction is that we also want to optimize the quantum circuit, because if your circuit is shorter or the depth is smaller, then you would be less affected by the noise. So that would also be a way to go. So that's it. Thank you. Close the event. Oh, sorry. Still have more. Yes.
I have one question. When you show us the momentum distribution, well, I actually expected to see something like the momentum distribution a long time, but not. I don't understand.
Oh, this is a good
That
question. Yeah. Yes. So. Yeah, that's a good question. So, I mean, here. I want to show the circuit. This is because when you do a measurement, you lose the state, you lose information. So we actually also did that, but I did not show it here. So if you want to see the process, like what the state is like, the intermediate state is like, right? Then you need to do measurement here. So if you want to see how the state evolves, if you are also interested in the intermediate process, you need to run one simulation and do measurement in the middle. And but you cannot, once you measure, you cannot continue with the same simulation. You need to do another simulation, and then maybe you do measurement at a later time. And also, and put all the information together, you can see the evolution of the state with the time sequence. That's what you do with quantum calculation. But if you calculate by solving the Schrödinger equation, then you can evolve your state to some time, and you see what the wave function looks like. But then with that wave function, you can continue to do the calculation. So that is one difference between the calculation classically and the computation on quantum computer. Okay. The questions, I think.